first. This is a tricky domain because, unlike simple arithmetic, to solve a calculus problem, and in particular to perform integration, you have to be smart about which integration technique should be used, integration by partial fractions, integration by parts, and so on. This is from Marvin Minsky, among the pioneers of artificial intelligence. This statement best subsumes the nature of computation in calculus. It is mostly rigorous and often mechanical application of methods and laws and identities of algebra and trigonometry. Of course, it is even more so for integration, the subject of this lesson. Integration, as the name indicates, is the reverse of differentiation. It is kind of antiderivative in its essence. If differentiation is about distinguishing every instant of change with instantaneous rate over an interval of change, integration is just the opposite, finding the total change in something over an interval or the entire domain of the function. Integration is about undoing the micro-detailing of continuous change, done with the help of instantaneous rate of change. Integration aggregates the changes over the instance to come to the quantity of resultant or net change. For example, integration of acceleration over time sums up the effect of increasing, decreasing, or constant acceleration at instance. This is shown as the decreased, increased, or constant velocity. The outcome of integration of acceleration is thus the net effect on the initial velocity, the starting velocity, due to the changing acceleration. Instant rate of change is actual quantity. But how does integration become the reverse of the process of differentiation? Unsurprisingly, it is in the simplest way. It uses the instantaneous rates of change over a period to get the information about the cumulative effects of those changes. The instant rate of change is added up for all the instants. It is easy to realize that the instant rates quantity are also the actual quantity of changes in an instant. Thus, the instant rate of change is important for integration too. The rate is the building block or the starting point for understanding how quantities change over time or any other variable. Recall, it is the slope of the tangent at a point that is the value of the derivative, the instant value of rate of change. Then what may be the equivalent of the same for integration? It is the area under the curve. Let us explore it next. It is quite a mystery for most. Revisiting graphs, curves. Before we get into exploring area under a curve and how it does contain the effect of change over a period, it would help us to get right three information. First, what do curves represent? Second, what does the y-axis represent? And third, which is the area under the curve? This is quite a den of confusion, even mystery, a personal experience. Curves, the generic name for graphs of functions, represent functions on a plane through an infinite series of ordered pairs or points on the Cartesian plane. Recall, functions are like processors, taking in inputs and offering a definite output for each input. The curve, that is, the line that is formed by connecting the points, strings together the values of the function, the outputs. The curved line and the x-axis. We make graphs to plot the output or the values of the function for numerous values of the inputs, the independent variables, to visualize the behavior of the outputs, the effect of the inputs. The y-axis represents the values of the function or the output for every input on the x-axis. The vertical length along the y-axis is the value of the function, the value of f of x, for every valid value of x, the input. Thus, the x-axis is the reference or the base over which the function values are measured or built. Expectedly, the height of the curve above the x-axis has a special significance. This vertical length is due to the values of the y-axis. The x-axis values are always along the horizontal x-axis. Relevantly, the distance between the x-axis and the curved line represents the action, the processing, the effect of the function. X-axis, foundation for the roof, the curved line. The origin of graphs, the 0, 0 ordered pair, is shared by both the axes. And being a vertical distance, the y-axis, that is the function values, take the x-axis as the 0 starting point or the baseline. The y-axis is counted over the x-axis. Thus, every function is what lies between its curve and the x-axis. By default, the space or area between the x-axis and the curve line does say something about the quantitative nature of the graphed functions. Importantly, the length of the curve line is of little significance because all real-world functions are valid over the set of real numbers. Thus, all curve lines are similar, that is, all are limitlessly long. There is little difference on this count among functions. It is the space between the curve line and the x-axis that is the only and the effective descriptor of the impact of functions. The input-output change is seen in this space. The curve line is why we make the graphs. Examples of area under the curve. To the point, this picture shows the area under the curve of the function f(x) equal to x. However, it may be added that we take the area under different quadrants separately because the integral values could be negative despite the area being a positive quantity. So, the area under f(x) equal to x may just be seen as the first quadrant area as shown now. This picture shows what is not area under the curve of f(x) equal to x. Similarly, this picture shows the area under the curve of the function f(x) equal to x squared. And this picture shows what is not area under the curve of f(x) equals x squared. It could be the space between 2 points, that is, an interval on the graph, or the entire domain of the graph. Area under the curve and integration. To keep it all simple, let us illustrate the relationship of area under the curve of a function and its integration through an example. And nothing can be simpler than exploring this relationship through distance and speed relationship. It is familiar as well as easily relatable, and we can be to the point. Recall, the rate of change of distance traveled over time is speed. That is, speed is derivative of distance. As also that integration is the reverse of differentiation, of finding the derivative. Thus, we will explore how is the area under a curve of speed or velocity is related to distance. The reverse of computing speed from distance. The graph shows a linearly increasing speed. It is a speed-time graph. The area under the line, the straight curve of the graph, is shown between the time interval 0 to 3 minutes. The interval is chosen to be able to measure a finite area under the curve. The question is, how much is the area under the curve between time 0 to 3, and what does that represent? The picture shows that the area is actually the distance traveled in 3 minutes. The area is simple, half into length into breadth, given that the area is a right triangle. Indeed, the integration or the reverse of derivative speed is distance. Distance is the integral of speed. We will keep it simple here and not explain further. Most importantly, it is universally true that the area under the curve of a function gives the integration of the function. Before we move on, we must know how exactly is the area of the triangle equal to the distance traveled. The triangle is the area under the curve of the speed-time graph for the chosen interval of time of 0 to 3 seconds. To the point, the area of the triangle, a right triangle, is half into 3 into 3, that is, half of 9 or 4.5 or 4.5 kilometer. Now, what is the distance traveled in the interval? From the graph, we can figure that out. The distance traveled in the first minute is half kilometer. In the second minute, it is 1.5 kilometer, and in the third minute, it is 2.5 kilometer. How did we get these distance figures from the graph? We will have to take the average speed in each of the 3 minutes of travel because the initial and final speed in these durations are not the same. The average speed in the first minute is 0 plus 1 by 2, that is 1 by 2, or half kilometer per minute. The average speed in the second minute is 1 plus 2 by 2, that is 3 by 2, or 1.5 kilometer per minute. The average speed in the third minute is 2 plus 3 by 2, that is 5 by 2, or 2.5 kilometers per minute. The sum of half, 1.5, and 2.5 is 4.5. It may now be appreciated why we took a linearly increasing speed time graph. It made the computation of the average speed easier, as just the average of the initial and final speed in all the three 1-minute time intervals. Relationship of rate of change and integration. The speed and distance relationship also shows how integration is about rate of change per unit of time, multiplied by the number of unit of time under consideration. In the speed time graph, if, for simplicity, we take 1 minute as the unit of time, then the average speed in every minute is the actual distance traveled in that minute. Recall, a speed of 60 km per hour implies a distance of 60 kilometers in 1 hour, and over 3 hours it becomes 3 into 60, that is 180 km of distance. Of course, in calculus, the unit of time is infinitesimally small, but the above fact holds true. The quantity of rate of change of distance, the speed in each of the infinitesimal time, or the instant, is also the distance traveled in that instant. Mathematically, it is written as fx dx. The power of calculus comes from making the time interval so small that in that interval there is no need to compute the average rate, and there is just one rate. The rate does not change in that period. In general, the rate at the end of the interval and at the start of the interval may be different if the interval is not an instant. Integration uses rate of change in infinitesimal periods. Of course, it does not have to be time, as the independently changing quantity. Integration works for any independently varying quantity, such as temperature sensitivity of chemical reactions. Examples of antiderivatives, integrals. Here are a couple of examples of antiderivatives in broad terms as being integration. Obviously, antiderivative or integration is operable on derivatives, derived quantities, by kind of undoing the derivation process to get the amount of change. For example, when we integrate speed, we get the net change in distance over the period. When we integrate acceleration, we get the net change in velocity in a period. This net change is the sum of the instant rate over all the instants. There is another view of the same. When we integrate speed and get net distance traveled, we also indirectly get the average distance traveled per unit time when we divide the net distance with the period. And when we integrate acceleration and get the net change in velocity, we also indirectly get the average velocity during the period by dividing the net change in velocity by the period. In general, simplified, the integration of a function is the average of the function it is derived from. Area and volume and density and mass share a similar relationship. The second quantity of the pair, volume and mass, represent the integrals. Here are some popular domain of knowledge that significantly need integration. First, area between curves. Second, distance, velocity, acceleration. Third, volume. Fourth, average value of a function. Fifth, work. Sixth, center of mass. Seventh, kinetic energy, improper integrals. Eighth, probability. Ninth, arc length. 10th, surface area. Integration and curved lines and spaces. Through the distance and speed example, we presented how integration is the net effect of continuously changing situations. By net effect, we imply the sum of increase or decrease in a changing quantity over the period, whatever it is. This is through the rate of change. The other significant application of integration is in measuring curves, lines, area, surface area, and volumes. We will now explore the basic principles of measuring length of curved lines, circumference of circles, volume of a straight cylinder, and area of the surface of a sphere. We only have to remember that calculus operates through functions. Thus, all we need to find the length of a curve is to functionalize the given curved line, to mathematically copy the shape of the curve. The following steps represent the most generic process of finding a function, that is, a mathematical expression that represents a curved lines. First, find a set of points on the curve that nearly represents the curve. A simple way of doing is to properly place the curve on a Cartesian plans and get the set of points that are on the curve. Second, find the parent function that best fits with all the points in the set, or compose new functions by mathematically putting together the parent's functions. Third, minimize the difference between the actual set of points and the function is chosen or composed above the least square. Fourth, use the function to find its length by integrating the function over the horizontal or vertical length. This is a simple task of integration process. Circumference of a circle. Finding the circumference of a circle follows the same principle as that of the length of a curved line discussed earlier. And it is much easier because circles are already well modeled as a function. For reference, there is an arc length formula that is based on the Pythagoras theorem, and that function is integrated for length that represents the full circle. Anything more will be unduly technical. Surface area of a sphere. This too follows the same principle as that of the length of a curved line. And it is much easier because spheres are very definite shape and well modeled. In the Cartesian plane, there is a sphere formula, and we integrate the infinitesimal surface area element dA over the appropriate ranges of two angles that define spheres. More details would be extra mathematical. Volume of a very thin straight cylinder. Being volume, it is a somewhat different computation. Most simplistically and conceptually, we can see the cylinder as being made up of infinite slices of circles, as shown in the picture. The area of a circle is known. We then integrate that area, the height of the cylinder. The area of this circle is a good approximation of the space within a circle. And after integration, it is a good approximation of the space over the entire cylinder. More detail is out of context. Integration is true to its name. It is a sum. Generically, it is the sum of the changes in changing things over a period or whole domain of a function. Specifically, but yet broadly, it is the sum of the infinite instantaneous rate of change, each over an infinitesimal period or other quantities. Precisely, integration measures the accumulated effect of the instantaneous rates of change, but the rate being equal to the quantum of change itself in the small period. Functions form the basis of integration. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.